Hello guys, welcome to my channel. Myself, Pressel. In this lecture series on electronics, I'm going to cover fundamental of electronics because this subject is taught in most of the engineering colleges in first or second semester. Now, this series is not intended to cover the particular university syllabus. It will give you the general focus on the most of the university is syllabus. Okay, so let's get started. So first question arises, what is electronics? Okay, so electronics is scientific and engineering discipline that deals with the theory and the use of device in which the electrons a vacuum, travel through a vacuum, gas, or a semiconductor medium. Okay, so basically, electronics deals with the flow of charge carriers in three mediums. One is vacuum, another is gas, and third is the semiconductor. And the most widely used medium is the semiconductor medium. Okay, these techniques were used in early days, and the vacuum medium was used in manufacturing the first computer. That was your ENIAC, and this ENIAC was designed by a vacuum tube that was a three terminal device. Okay, and father of electronics is the Michael Faraday is the father of electronics. Okay, so some of the electronics components are shown in this slides. You can see this is your vacuum tube that uses a medium of vacuum, and this is diode, and this is transistor, and this is integrated circuits. The diode, transistors, all the integrated circuits that uses the semiconductor medium. That means the most widely in the modern day, the most widely used medium is the semiconductor medium, and semiconductor medium provides peculiar properties that made it to be used so widely. Okay, so second question is what is difference between uh, electrical and electronics? And so the first criteria of difference is the definition. What definition tells? Basically, electrical technology deals with generation, distribution, storage and conversion of electrical energy. But electronics technology does not deals with the generation, storage, and conversion of electrical energy. Basically, it deals with designing, amplifying, and switching the electrical energy with the help of different electronic devices. That means an amplifying, and that means most of the processing and controlling action is performed by the electronics equipments. Okay. Next criteria for the distinction is fundamental role. In electrical circuit, electrical energy consists of flow of electron. So only the electron is the charge carrier, and that is responsible for flow of electrical energy into any of electrical devices. That is only electron. But in case of uh, electronics, there are two charge carrier that provides the flow of current and flow of electrical energy into the electronics devices that are electron and holes. And that means there are two charge carrier available. That's why that provides the controllability and processing capability of the device. Okay, if you talk about the device principle, that means it works on which kind of voltage or current. So electrical devices produces a voltage and current, but electronic device control the voltage and current, and mainly it works on the DC voltage and current. Okay, current functions AC or DC. Already told you it works on the alternating currents, and basically in alternating current maybe single phase, three phase, or maybe in volt or kilovolt range or megavolt range. But only electronics devices only works on the DC, and the range of voltage is very few, millivolt to volt, and general rating is generally 5 volts. Most of the devices, the electronics uses 5 volt, 12 volt, and maximum 24 volts for their operation. Okay, If you talk about the conducting material, okay, so in electrical, only the conductor, yeah, conductor is used, okay, and the copper, aluminum are the best conductors. But in electronics, only semiconductors is used in the electronic circuit in modern era, okay, and mostly the semiconductor materials that are silicon and germanium, and there are some compound semiconductor materials, okay. A specification of components wise, that means electrical consist of only the passive component, okay, but electronics consist of active components. So what is the passive and active components, we will see in the next slide, okay. Next is a function. The electrical devices cannot manipulate data, but electronics divided can manipulate data to time. Electrical power, if you see the electrical power, uh, the electrical circuit, the role is to control, monitor at the high electrical power, but electronic circuit monitor and control the low electrical power, okay. So the next point is your decision making. Electrical devices cannot make decision, just electrical cannot make any kind of the decision, but electronics devices, they easily can make decision. Best example of the electronic device, you can mobile, uh, and so many devices nowadays. Most of the devices that you will see in your hand, smartwatch, that is also an electronic device. Energy conversion, but electrical devices perform the energy conversion. That means energy conversion in the form of electrical conversion, other forms of energy, that means heat, motion, but it does not convert into other forms, okay, mostly, okay. If you see the size and weight, the electrical devices occupy is of large size, and mostly the large weight, okay, heavy weight, and occupy more spaces to be placed, okay. But electronic devices, in miniaturized devices, it is available in a small size that you can actually transport electronic circuits, pieces of equipments. It requires very a small size for their placements, okay. So examples are transformer, ultra electrical device, example alternators, motor, generator, fuse, circuit breakers. These are the example of electrical devices. Diode, transistor, integrated circuits, microcontroller, microprocessor. Most widely used, you have find the microprocessor, uh, and RAM. You might have heard about the RAM. These are all the electronic devices, okay. So already told you the major components. The all the components are divided into two categories. One is the active components, another is a passive components, okay. So active components, the components which active components are the components which supplies uh, energy to a circuit, okay. Energy to a circuit, that means it performs the action of amplifying, rectifying, converting and supplied electrical energy. So you can see the voltage source and current source, what it is doing, it is supplying the energy into the circuit. Generators, this is also a kind of the active components, okay. All the semiconductor devices, such as bipolar junction transistor, MOSFET, FET, JFET, diodes, all are the active components because they supply energy to our circuits, okay. But the passive components is components which can only receive energy or receive energy. And how they receive energy, it either dissipate energy, absorb energy, or store energy. Dissipate, absorb, or store energy in the electric or magnetic field, okay. As the name passive suggests, passive devices do not provide gain or amplification. Passive cannot be used to amplify, oscillate, or generate electrical signal. These are the example of the passive device. Resistor, inductor, capacitors, and transformers are the example of passive components. So, what is the electrical device? Electronics device. Sorry. What is the electronics device? The electronics device are the component for controlling the flow of electrical current for the purpose of information processing and system control. Okay, so role of any electronic device is what it performs this information processing and system control. That means the processing of signal and controlling the uh, other devices. That is basically a that is the work that is basically performed by any electronic device, and this thing is being done by controlling the flow of electrical current by controlling the charge gradient. And there are two kind of charge gradient in all the electronics devices. One is a electron, another is hole. So you can see this is your transistor, this is integrated circuits. Okay, this is uh, okay, and this is your diodes. These are the some electronics devices available in the market. So first question arise, what is electronics? Okay, what is semiconductor material? Semiconductor, already told you, semiconductor is most widely used material, and uh, because of this material, the electronics will gain so much popularity in information processing and controlling the devices. Okay, so what is the semiconductor material? Already know the semiconductor is a special class of element having conductivity between a good conductor and insulator. That means its conductivity lies between the perfect conductor and insulator. The semiconductor material is available in two forms. One is a single crystal or elemental form, also known as also it is elemental form. Okay, single crystal or elemental form and compound form. Single crystal, that means it has only one kind. It has only one types of atoms, and it has the atoms of two different two or more elements. Okay, so most widely used single crystal semiconductor materials is germanium and silicon. Okay, and these are the compound semiconductor material: gallium arsenide, cadmium sulfide, gallium nitride, gallium arsenide phosphide. These are the most widely used compound semiconductor. Semiconductors are formed by the covalent bond. That means in order to form the bond, a force between the two neighboring atoms, they share the electrons because its outermost orbit has 4 electrons. Okay, so silicon, the atomic number is 14. Germanium, the atomic number is 32. Both are the tetravalent atom. Its outermost orbit has 4 electrons, and due to that, they share the neighboring atoms in order to form the covalent, a strong bonding between the two atoms. These are some example of the trivalent and pentavalent, uh, trivalent and pentavalent impurities. Okay, gallium arsenide. Basically, we will use this is basically the trivalent atom, and this is basically your pentavalent atom. Okay, so this is the structure of the single crystal silicon and germanium. Okay, the covalent bonding between the silicon single crystal silicon atoms and the covalent bonding between the single crystal germanium atom. So in pure silicon or germanium crystal, the 4 valence electron of one atom form the bonding arrangement with the 4 adjoining atoms. That means each atoms of the single crystal silicon, it forms the bonding between the adjoining four adjoining atoms. Okay, the bonding of atom is strengthened by sharing the electrons, and this is called the covalent bonding. Already know the sharing of electron forms the equivalent bonding. So again, in germanium, you will see each germanium atoms is the shared by the 4 adjoining atoms. Okay, 4 adjoining atoms. So this is the example of gallium arsenide. Gallium arsenide. Okay, this is a compound semiconductor, and there is sharing between two different kinds of atom. Okay, you will see sharing between two arsenic and gallium. Okay, so you can see there is a complementary approach of sharing. That means each arsenic atom uh, 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 is shared by the 5 gallium atoms. Okay, and that means and each gallium atoms is shared by the 3 arsenic atoms. Okay, in this way the covalent bonding is formed. Okay, the each atom's gallium or arsenic is surrounded by the atoms of complementary type. That means gallium is surrounded by the arsenic, or arsenic is sun. There is a still sharing of electrons similar in the structure of the gallium arsenic, but now the 5 electrons are shared by the arsenic atom and 3 by the gallium atoms. You can see in the structure. Now the comparison between the gallium silicon and germanium, silicon, and gallium arsenide. And these were the most widely used materials for the construction of the semiconductor devices. So, in early days, in exclusively the germanium, few decades after the invention of diode in 1939 and transistor in 1947, the germanium was the most widely used material. The cause of most widely used first uh, first is the cause of most widely used first is the purity. That means purity of obtaining the material, and second cause, that means it was easily purified by the existing instrumentation system available at that moment. Okay, and also it was available in large quantity. Okay, large quantity. So this was the most widely used material in the early days, but it has some disadvantage. Uh, it suffers from a low level of reliability because it is less reliable, because it has a more sensitivity to the change in temperature. That means temperature changes, its characteristic will change. That means it is more sensitive to temperature, and the stability of the devices formed by the germanium was not very good. Okay, so the alternative material were thought at that moment. Okay, the silicon material has basically the improved temperature sensitivity, but the refining process of the for the manufacturing the silicon of very high purity level was still in development state, because at that moment the instrumentation system was not advanced. So getting the high purity material was not possible at that moment. So finally, the first silicon transistor was manufactured in 1954. Okay, so one important property of the germanium was obtaining the a high level of purity, and second was it was available in large quantity. So due to the advancement in the instrumentation system, it was possible to obtain the high purity silicon crystals. So finally, in 1954, the first silicon transistor was introduced. Silicon is not only less temperature sensitive, but also one of the most abundant material on the earth. Okay, on earth in the form of silicon dioxide. Silicon dioxide. The silicon is uh, in the form of silicon dioxide. Uh, it is available in it is available on the earth, which can remove any concerns about the availability. That means earth has very a large quantity of silicon in the form of compounds, silicon dioxide. Okay, so this was at that moment this was the single crystal semiconductor material, but these material was not much faster, and day by day the speed was a major concerns of any electronic devices. So people started thinking about the alternate semiconductor material that provides the better speed than the germanium and silicon. Okay, so as the field of electrons became increasingly sensitive to the speed, the computer were operating at a higher speed, and communication system were operating at high level of performance. Then the gallium arsenide was At that moment, the gallium arsenide was found as the semiconductor material capable of meeting the higher speed needs of the moment. So the first gallium arsenide transistor was developed in 1970, as that has the speed 5 times more than silicon. Okay, so advancement in the semiconductor compound semiconductor technology was done due to the needs of providing the speed of the electronics devices. So what happens? The covalent broke in. Okay, whenever a covalent of the silicon crystal broke, when it gains the energy from external sources, okay, in the form of light or heat. Okay, so external causes provide the bond breaking, and due to bond breaking, what happens when this bond break, the electrons will leave the place and a vacancy will be created here, and electrons become free. Again, this bond break, electrons leaves the place, a vacancy is created, and a free electrons has been found. Okay, so the vacancy is called hole, and the free electrons that moves in the crystal is called free electrons. So always you can see whenever the bond break, the electrons and holes always occur, always generated in pair. Okay, so electron and holes are always generated in pair due to bond breaking. Okay, and at room temperature, approximately the concentration of the charge carrier in 1 centimeter cube of the intrinsic silicon semiconductor, and that is 1.5 into 10 to the power 10 charge carrier. That means number of electrons and holes. So creation of free charge carriers always happen due to the bond breaking. So all the covalent bond will result in a stronger bond between the valence electron and their parent atom. It is still possible to electron to absorb some kinetic energy from the external natural causes to break the covalent bond and assume the free states. Okay, and the generation of electrons or holes always occur whenever your semiconductor material gets some external energies in the form of light or heat, and bonds started breaking, and electrons and holes are always generated in pair. So you can see electrons and holes are always generated in pair whenever the bonds break. So here the flow of electrons or holes in semiconductor material. Now you see, this is the semiconductor materials in the crystals. Okay, silicon atoms are shown, and there are outermost their shells are being also shown. So you can see when the battery is connected with the any semiconductor material, what is happening whenever a vacancy has created, the electrons is filled from this terminal, and again the next the electrons is going forward and forward. But if you closely observe what is happening in about the holes, the blank space, it is going backward. You can see it is going backward. Again, this this is going backward. That means the direction of flow of electron is opposite to the direction of flow of holes. Okay, so this picture, the direction of flow of electrons is this. Okay, and direction of flow of holes is just opposite to the direction of flow of electrons. So convention direction of currents, already you know, the assumed to be opposite to the flow of electrons, but the convention direction of current due to holes is in the direction of hole flow. So you can see the direction of current due to electron is in this direction, and direction of current due to hole is also in this direction. If we apply KCL at this point, this I is the total current, I is the incoming current, and IE and IH, the current due to the electron and current due to the holes, is a leaving current. So the total current IE plus IH, the total current will be the sum of current due to the electrons and holes. Okay, so always in semiconductor material, the current current is being caused by two kinds of the carrier. One is the hole and the another is electron. Okay, The next topic is types of semiconductor material. So there are two types of majorly it is classified into two types. That is one is the intrinsic semiconductor, another is the extrinsic semiconductor. So intrinsic semiconductor is the purest form of the semiconductors that is obtained by the existing instrumentation system. Okay, so term extrinsic intrinsic is applied to any semiconductor material that has been carefully fully refined to reduce the number of impurities to the very low level, essentially as pure as can be made available through the modern technology. That means the modern instrumentation systems that provide as pure as as uh, and that means as pure as possible level of the purity obtained by the existing modern technologies and okay, so intrinsic semiconductor is the purest form of the semiconductor that is obtained by the today's modern technology. When this intrinsic semiconductor is added by some impurities, that is trivalent and pentavalent impurities, that means in semiconductor material two kinds of impurities are added. One is the trivalent impurity, another is pentavalent impurity. That means the trivalent impurity, the impurity that has valence electrons. The atoms of this impurity has three electrons in their outermost shell. That means three valence electrons. That is why it is named as the trivalent impurities. Indium, gallium, and aluminum and boron. These are the trivalent examples of the trivalent impurities. And pentavalent impurities. That means nitrogen, phosphorus, arsenic, antimony, and bismuth. These are the examples of the pentavalent impurities. So the pure semiconductor, in order to increase the conductivity of the pure semiconductor, that means in the pure form the semiconductor is not much conductive. So in order to increase the conductivity of the pure semiconductor materials, we intentionally add the trivalent and pentavalent impurities according to the requirements, and this process of adding the impurities is known as doping. Okay, so doping is what? Doping is the introduction, intentional introduction of the trivalent and pentavalent impurities into the intrinsic semiconductor for the purpose of modulating its electrical, optical, and structural properties. That means mainly the electrical and properties are being modulated by adding the controlled amount of the impurities into the pure or intrinsic semiconductor material. So how much impurities are added? Few number of impurities are added. That means you can see a one one impure atom in 1 million the atoms of the pure semiconductor. That means 1 ppm, 1 part per millions, 1 part per billions. In these numbers, the impurities are added into the pure semiconductor material. So after adding the impurities, the semiconductor materials obtained is known as the extrinsic or impure semiconductor material. And also it is also known as and there is also another name, that is the doped semiconductor. Okay, that is doped semiconductor material. Okay, the semiconductor that are doped with the specific impurities that modify the electrical properties of the semiconductor and makes it more suitable for the electronics devices such as diode, transistor, and etc. Okay, so doped semiconductor or extrinsic semiconductor is impure form of the semiconductor, and that is this impure form is not an unintentional form. This is the intentionally impure form of the semiconductor material. And why we are adding the impurity in the pure semiconductor in order to increase its electrical properties. Okay, so what extrinsic semiconductor, what doping is doing? Doping is doing basically, doping is increasing the carrier concentration, hence the conductivity of material. Okay, so what kind of impurities? Already told you there are two kinds of impurities are added. One is the trivalent impurities, another is a pentavalent. No other impurities are added in the semiconductor material. So if you add the trivalent impurities into intrinsic semiconductor, then the so form extrinsic semiconductor has a specific name. If we add the pentavalent impurities in the pure semiconductor material, the extrinsic semiconductor material so formed after adding the pentavalent impurities is also known has some special name. Okay, so yeah, there are two kinds of extrinsic semiconductor or impure semiconductor according to classified according to the adding of trivalent and pentavalent impurities. So addition of doping of or addition of the pentavalent impurities into an intrinsic semiconductor creates the n-type semiconductor, and addition of trivalent impurities into the intrinsic semiconductor creates the p-type semiconductor. So if you add the pentavalent impurities to the pure semiconductor, it will form extrinsic semiconductor whose name is n-type extrinsic semiconductor. And if we add the trivalent impurities in the pure semiconductor material, then it is named as p-type semiconductor material. Okay, so if we see this is antimony. Okay, so and its neighboring atom is silicon atoms. So you can see there is some extra electron here, that is the fifth electrons. Okay, and rest 4 electrons is shared by the neighboring silicon atom. Okay, so if this bond break, a vacancy is created here, and a free electron is created, and this is not attached with any bonds. So a small amount of energy is provided to this crystal, it becomes free. Okay, so whenever the bond is break, a hole on electrons is created in pair, but this antimony is providing the extra electrons. Okay, so if this bond break, what happens? A hole is created here and electron becomes free. Okay, so if we see in this case what is happening, 1, 2 and 3, there are 3 holes, 1, 2, there are 2 holes, there are 2 holes, and 1, 2 and 3, there are 3 electrons. That means in majority you will find the holes is available, and in electrons is available, and in minority you'll find the holes is available. So who is responsible for creating the this unbalance in number of carriers? That is if that is your this pentavalent impurities. That is why it is also known as a donor atom. This atom is known as because it is donating electron, because it is donating electrons. So in uh, uh, n-type semiconductor material, when it donates electrons, the what kind of charge comes on this antimony? That means positive charge. So this in this crystal, n-type crystal, you can see these are showing the a okay, the ions of the donor ions, because the atoms of antimony is donating some electrons, so it becomes ion, and ion is an immobile charge carrier. It will not be mobile, and it will not be responsible for that means creating any kind of current. Okay, these are the free electrons. Okay, these are the free electrons, and these are the free holes in the lattice of the n-type semiconductor material. So in in n-type semiconductor material, the number of electron is greater than number of holes. So number of electron is a majority charge carrier, and number of hole is minority. And then that means the electron is the majority charge carrier and hole is minority charge carrier. But in p-type semiconductor, okay, the addition of trivalent impurities and an intrinsic semiconductor creates the deficiency of valence electrons, and that means creates the extra holes. So you can see when there is no bond is broken, still due to this trivalent impurity, a vacancy is created here, and that means an extra hole is already created there at this place. Whenever a bond is breaking of bond creates generation of electron and holes in pair. So electron will release and a vacancy is created at this place. So always what you are observing, the number of holes is always greater than number of electrons in this case. Since this trivalent impurities needs some electrons to obtain the structure of inert gases and becomes stable. Okay, so it will take electrons from the neighboring atoms and becomes stable. So when it takes this free electron, okay, that means it is accepting the electrons and becomes negative ions. Okay, then this becomes negative ions, that is known as the acceptor ions. Okay, This is when it becomes ions, it is immobile ions. Okay. So always in this case, you will find the number of holes is always greater than number of electron. So hole is the majority charge carrier and electron is the minority charge carrier in case of the p-type semiconductor material. Okay. So majority charge carrier is direct number, that means concentration of majority charge carrier is directly proportional to doping. That means higher the doping, the majority charge carrier will be higher. Okay. A minority charge carrier is inversely proportional to doping. That means higher the doping, lesser will be the minority charge carrier. Okay, that means in n-type semiconductor, if we increase the doping, okay, so the number of electrons, that is the majority charge carrier, will increase and number of holes will decrease. But in p-type semiconductor, if we increase the doping, number of electron holes, that is the majority charge carrier, will increase and a number of electrons, that is minority charge carrier, will decrease. Okay. So in any intrinsic semiconductor, the number of electrons in conduction band or the number of holes in the valence band in any intrinsic material, uh, uh, this number of the carrier depends upon the band gap of the material and on the temperature. So what is the intrinsic charge carrier concentration? That is the number of broken bonds per cubic meter. That is the intrinsic charge carrier. So whenever the bond is break in a pure, that means intrinsic semiconductor, the electron or hole always generated in pair. Okay. So Ni, this Ni will be product of what? N into P. Okay. That means N into P. Now what happens? N is equals to P is equals to what? It becomes Ni, because the number of bond brokens is equals to number of holes and number of holes. Okay. In this case of the intrinsic semiconductor material. But in case of the extrinsic semiconductor material, uh, number of electrons or holes is not equal, but still it follows the mass action law. Okay, whether it is the extrinsic semiconductor or intrinsic semiconductor, it always follow the mass action law. In a semiconductor, whether it is intrinsic or under thermal equilibrium, the product of holes and electrons will always be constant. Product of holes and electrons and is equals to the square of intrinsic carrier concentration. Okay, that is Ni. The N into P is always Ni square. Okay, it is very much visible in case of the intrinsic semiconductor. Okay, N is equals to P is equals to, that is Ni. So N into P, if you do, that is becomes what? Ni square. But also in case of there is a dissimilarity between the number of holes and electrons in extrinsic semiconductor, but still it holds. In case of n types, n is greater than p, but in case of the p type, n is less than p, but still it holds the n into p is Ni square. Okay. So if you see the flow of electrons in this is your n-type semiconductor, and this is your p-type extrinsic semiconductor. So let me. So what is happening? This extra electron becomes free after getting some, and whenever the bonds is broken, the electrons or holes is always generated in pair. Okay. So you can see in this video, this electron is released from the phosphorus and bonds is broken, electron and hole pair is always generated in, electrons and holes always generated in pair. Okay. In this case, there is a vacancy here. You can see there is a vacancy and this bond is not formed. So what happens whenever a bond is broken, what happens? This vacancy will be filled, and again bond is broken, electrons and holes are always generated in pair and fills the remaining vacancy, and this process continues in order. Okay. Okay. See, this is filled. Again the vacancy is created again. Again this bond is broken. Okay. Then again this bond is. That's all. If you like the videos, please do subscribe, share, and